Welcome back to part 4 of Module 201B. In this video, we're going to take a closer look at the relationship between sine waves and phasor diagrams. If you remember, we discussed earlier what a phasor was, a phasor being a representation of the magnitude of an electrical property, and that property could be voltage or amperage. When we represent a phasor, that tells us how much that current or voltage is there. And as we place that phasor on our circle diagram, representing 360 electrical degrees, the degrees tell us its relationship to another electrical property within the same circuit. So we could have a phasor for voltage and a second phasor for current, and the angle between the two would represent the time lag that we'd have between those two as well. When it comes to our sine wave is a representation of the sine of the angle of difference between those two values. So if we use our reference line of 0 degrees and our phasor was at 45 degrees, our sine value on a sine wave is the sine of 45. And that would tell us where exactly we are on the sine wave at any time. Before we go any further, I will remind you of some of the standards that we use for drawing phasors. The horizontal axis is used as the reference, and the degrees of time go counterclockwise from 0 to 360, which would complete our circle. Anytime that we have a phasor with a closed arrowhead, that represents current. Anytime that we have a phasor with an open arrowhead, that represents voltage. And at any point in time, we should have one of our values on our reference line at 0 degrees. Normally, that depends on the type of circuit that we have. Since we've been talking about series circuits, we would have our current as our constant, therefore our current would go on our reference line. There are two different terminologies that we need to understand when we talk about sine waves and phasor diagrams. The first one is called in phase. When we have two phasors on a phasor diagram or two phasors within a circuit, if they both cross the zero line and they peak at the exact same time, then they are called to be in phase. So when we look at the sine wave diagram, we should see the arcs of both the two values being exactly the same, although maybe they have different magnitudes, different peak levels, but yet the peak time would be the exact same. On a phasor diagram, we would see both the phasors on the exact same angle. Typically, when we have a resistive circuit, both of my phasor diagrams would be shown on the reference line. And that means that my current and my voltage and all the other currents within that same system are all at the same angle. The opposite of being in phase is being out of phase. And since in phase is everything lining up with each other for the zeros and peak values, when things are out of phase, then they are either lagging or leading. And what we find is that they don't cross the 0 point at the exact same time, but rather there's a time period between when they do that. On my sine wave, I can represent both of the sine waves on the same diagram, and one will be either before or after the other. When I represent those on a phasor diagram, I'll be able to have one of those values on my reference line at my 0 degrees, and then the other value will be off 0 degrees somewhere. And that represents the angle of difference between those two, or the time difference between those two phasors. When we are talking about our out of phase components, we need to be aware of the terminology lead and lag. Lead and lag has to do with the relationship between two different phasors and how far apart they are for their starting times. Anytime that things are out of phase, they're not crossing the 0 point at the exact same time. When we represent that in a sine wave, we see that on the upper portion, V1 is crossing the median line at 0 degrees, but yet V2 doesn't cross the median line until 90 degrees. So when we look at that on a phasor diagram, we have V1 sitting on our reference line. Therefore, we say that V2 is lagging V1, because if we think about the counterclockwise revolution of my phasor diagram, V1 would cross that zero line before V2 would. On the second page, we also have the exact same phasors on our sine wave diagram. However, when we look at our phasor diagram, you'll see that we changed the reference. Now my reference is V2. So now I can say that V1 leads V2. So whether something is lagging or leading all depends on what we're using as a reference. In our circuitry, normally we're going to use whatever's our constant. So in a series circuit, we're going to use our current as our reference. So therefore, we're going to show our voltage as a leading or lagging value towards our current. So that would tell us where our voltage should go on our phasor diagrams. You've now reached the end of part 4. What I want to make sure that you understand is how to represent your phasors on your diagram, whether it's an open arrowhead for voltage or a closed arrowhead for current. And I want you to understand the idea of in phase, being everything's at the same phase angle, or out of phase, and whether that out of phase component is either leading, it's ahead, or lagging, it's behind, whatever is on the reference line. Once you've finished this, go back to Blackboard, complete the knowledge check, and then you can continue on to part 5.